Old school. Old school question. Back when you thought physics was hard originally, and then you realized, no, that wasn't the hard stuff. Remember way back when? That should be very straightforward for you to do. Use whatever resources you need, except let's try and keep it like just looking up the equations you need for this, shall we? But I was looking for two answers. Can you do them? And then I'm gonna have a part two to this. So this is just this is part one. I'll give you part two in just a minute. So if you remember good old-fashioned motion equations, you would have gotten an acceleration of 0.833 meters per second squared, and it took 24 seconds. You just needed to pick the appropriate motion equations, which in this case would have been 2 a delta x equals v squared minus v naught squared. That would have given you the acceleration. And if you were shooting for the time, I think I would have gone delta x equals 1/2 v plus v naught times t. Of course, if you had solved for t or solved for a, you could use one of the other equations as well, but this would work without having solved for anything ahead of time. Over here, the acceleration is the rate of change of the velocity, so you have to take the derivative to figure out the acceleration. So that's going to be 4 times t to the 1, so bring the 1 down. 4 t to the 1 minus 1 is t to the 0. Minus, bring the 2 down. 2 times 6 is 12. T to the 2 minus 1 is just t. So that's going to be the acceleration, taking the derivative. If I want the position, I have to remember that velocity is the rate of change of position. So I need to take the antiderivative to figure out the position. Starting with my term, my new t is going to go t to the 1 plus 1, or t to the 2 squared. Divide my 4 by 2 and get 2. Minus, t will go from t squared to t to the 2 plus 1, or t cubed. 6 divided by 3 is 2. But I also need to add, since I don't know where the object began, I need to add a constant here to remind me that there was an initial position that I may or may not know where that is. Okay? So we've done these before. If you don't remember these, you will need to practice because of what we're going to be doing today. We already had a long, drawn-out discussion about the relationship between these different variables. I need you to recognize that for every translational variable, there's probably a rotational variable that's similar. When we talk about an object's change in position and want to kind of apply it to an object that spins, the analogous or the parallel idea is that instead of it being a location, it's going to be a direction. It's going to be a change in the direction that it faces. We use angles to describe the direction something faces. So if I have delta x as change in position, delta theta would be a change in the direction the object faces. Right? So we're talking about it was facing one direction and then it's changing another. So I'll have final direction that it faces, final angle, minus initial angle. This stood for initial velocity. And this is usually the velocity of our interval, so final velocity. For something that spins, we're going to have a similar variable, except instead of using v, we're going to use a Greek counterpart. And one of the things I should probably just throw out there from the beginning is that almost all of the rotational variables are going to use some kind of Greek letter. So that's kind of how you can be clued in that we're dealing with something that's talking about rotational motion, because we'll have Greek letters to describe its motion and not our standard Roman letters for our motion. So for initial velocity, we're going to have omega naught. And omega is just like a lowercase letter. So let's get a look at our little elementary school thing here. Want to know what our letters look like? Omega is all down there, right? It's a lowercase letter, but it's got a little flare, so you can let the flare come above the top line, but that's the way it should be written compared to other letters. Theta actually is tall enough to be all the way up there. It should take up the whole line. So when you write omega, remember it's like a V, except it's got flare. Good so far? So I'll have omega naught and omega. This represents initial rotational or angular speed, velocity. And this will be final rotational or angular velocity. It could be either word. They could say rotational velocity, they could say angular velocity. They mean the same thing. A is just going to transition to alpha. So where A was our acceleration, we now have angular acceleration or rotational acceleration. Angular acceleration is used way more prevalently than rotational acceleration. And alpha, like in A, is also a lowercase letter, should exist all the way below the dotted line. So you compare it to other letters, this is what it should look like. Now, alpha and A look very similar, especially if you write in cursive. Try and differentiate, understand their meaning. These are all vectors. That part's going to become exceedingly important here real soon, but I'm going to leave the vector part of this out for just a minute as we just talk about what it is we are measuring. So the last thing is going to be T for time, but we're not going to use anything Greek there. Time is time, regardless of which of these things we're talking about. So there's a clear analogy here, and I hope you see this analogy, that we just have a replacement for each of the letters here. So for things that are behaving in a manner that's rotational and not translational, you will use the rotational letters. But all of those rotational letters, they mean the same thing. So if we had, let me put this here. If we had for linear, V equals AT plus V naught, do you realize there's got to be an angular relationship that's going to be the same? I mean, we just kind of saw it here with the thing that was spinning. It started with an angular speed of 0. It reached some other angular speed after some time. So there's clearly going to be a similar function for an object's angular speed, just like its linear speed. And I have no intention of putting some graphs in front of you, finding the area under the graph, and we're just replacing letters here, folks. It's going to behave the same way. In fact, take a moment. You should write out the 5 motion equations as they should appear, but with rotational letters, not translational letters. Please try it. All right. Again, don't want to spend a lot of time on it. You should have a group of functions that mimic what we used first semester, right? 5 motion equations. You're just replacing V with omega, delta X with delta theta, and A with alpha. It's all the same vocabulary. There are some things that will be a little different. For example, we can measure delta theta in degrees, rotations, revolutions, or radians. Degrees will be less likely, but the other ones will be very, very much exchanged all the time. You'll just need to be able to convert from one to the other. We did talk about converting from radians to rotations already first semester. It just involves 2 pi. You should be okay with that. Our initial rotational angular velocity, these are going to be RPM, RPS, radians per second, and to a lesser degree, degrees per second. But we won't use degrees hardly at all for this. It's almost always going to be rotations per minute or rotations per second. That is the most likely way you will talk about rotational speed. But the standard way, the way you calculate things like energy and such, is going to require that you always be in radians. Radians is like meters. So being in radians is the best way to do these. Angular acceleration is almost exclusively radians per second squared. Very seldom we'd be asked to put it in any other unit. And because this is angular motion, but it's really the same as what we've already discussed, it is also true that alpha is d omega dt, and that omega is d theta dt. So just like we studied first semester, we have an entire group of things that have a parallel measurement. And it's just rotational kinematics as compared to linear kinematics. So we just observed that thing spinning. Let's see, delta theta was 6 rotations. Omega naught was 0. Omega final was unknown. Alpha is unknown, but it seems like it took about 12.8 seconds to get there. I want the final speed in rotations per minute, and I want the angular acceleration in radians per second squared. You'll need to use one of those motion equations to figure out the answer. We've written everything out here. Take a few seconds and see if you can work out those two answers. If you can't, you're going to need to practice. If you can, you probably won't have to practice. Give it a shot. Let's see what you can do. Let's start with the first one. I want to calculate the acceleration. I want my answer to be in radians per second squared, so I need this in radians before I move forward. Or I could convert my final answer, but I'm going to convert this answer right here to radians. And I know that there's about 6 1/4 radians in every one rotation, because a rotation is 2 pi radians, right? You guys do have that conversion already? Talked about it first semester. So 2 pi is about 6.28. So 6 times 6.28 gives me 37.68 radians. And we talked about unit multipliers last semester, so if you need to do it the long way, do it the long way. But I would start wrapping your head around the idea that one rotation is about 6 radians. Get an idea for the numbers. So that's how many total radians it makes when it spins around. I'm going to use delta theta equals 1/2 alpha t squared plus omega naught times t. So 37.68 equaled 1/2 times alpha times 12.8 squared. You work that out. Alpha is going to be about 1/2 a radian per second squared. Any problem with that? What?
What was the conversion for rotation? There was one rotation.
One rotation is 2 pi radians. Well, I'm going to leave this in rotations and do the next one to find out the speed in rotations per minute. So I can leave it in rotations. The problem is my time is in seconds. So whatever answer I get, I'll have to convert to minutes. But I can use a relationship that I already have. I can use, let's say, delta theta equals 1/2 omega plus omega naught times t. That one works best for me. That'll be 6 equals 1/2 omega plus 0 times 12.8. So this gives me that omega equals 0.9375 rotations per second. That can't be my answer, though. I need a rotations per minute. So a unit multiplier here tells me that 60 seconds is 1 minute. So if I multiply that out, 56.25 rotations per minute.